Let's talk a little bit about chemistry and atoms. So again, just take a couple of things here, write down, but we're studying chemistry. Maybe some of you would rather say, I'd rather run away out of here. I don't want to know anything about this. It's torture, this chemistry stuff. Well, it's not. Chemistry, okay, can be something very amazing, very beautiful, okay, in the world that God has created. Helps us to enjoy the world. Everything is made up of atoms. Everything you see around us, okay? In fact, Faith, you got any of those candies left, or they're all gone? Oh, never mind. We'll come back to those. But anyways, chemistry can be very beautiful and very amazing. Okay? It does take a lot of study and a lot to understand, but it's how everything is made. Okay? How can you take something, let's think of a computer 10 years ago, large and big, and now you can get something, that same computer, into a little thing like a phone that your mom and dad may walk around with, to our iPads. Everything is made of atoms. This wood in the desk, the metal, your brains, your hair, your clothes, water, the food you eat, everything is made up of atoms. So it's all the same, right? But how can it be so different? Would you say, Logan, your hair is much different than chocolate that you eat tonight? Would you rather have for dinner? Hair or chocolate? Chocolate. So there must be some difference, right? Must be. Okay. So we've got to figure out what that is. Well, it's really the science of three different particles. Okay. Protons, neutrons, and electrons. And we're going to take a look at those. Today, specifically, we're going to focus more on these two because we really got to treat electrons much differently. Okay? But everything is made up of, so atoms, okay? Maybe I could do that here. An atom is made up of these things. So if you want to make a visual image, visualize a garbage bag. Blow it up with air, right? Hold it. It's a big ball. That's an atom. And anything you have inside would be protons, neutrons, and electrons. Those things inside of it make up what's an atom. Okay? So protons, neutrons, and electrons, they are what make up everything. Those three things, now scientists have found smaller things called quarks, but we're not going to get to that. That's for high school chemistry and college chemistry, beyond that. Here, we're going to focus on protons, neutrons, and electrons. So you can think of, I don't know, when you think of chemistry, maybe you think of mad scientists, right? What are mad scientists doing in the lab over there? Joe, what are they doing? Yeah, mixing chemicals, blowing things up. That sounds fun, right, Jesse? Okay, Jesse'd like to pour some stuff together, see what blows up, till it burns us or ruins us or whatever. Okay? But chemistry is involved in everything. Medicine is very important. How many of you would like to catch a disease and die tomorrow? Not me. Okay? We would expect if I catch a disease or if I get sick, I go to the doctor and he gives me pills, but really they're chemicals mixed together. Atoms and molecules forming together to make something so that those chemicals go into my body and fight the bad chemicals that are in there, trying to get away from them. Okay? Again, really neat. Okay? How does that work? It's something that's really David and Goliath and this guy, Dr. Emil J. Friedrich in here. Okay? What's cancer? Well, cancer is basically cells, which are made up of atomic particles. It's chemistry gone bad. It's killing things in our bodies. How many of you would go home, go to under the sink or go into the cleaning closet and find a big jar of poisonous chemicals, got the skull and crossbones, don't drink, and you dump that into your system today? Would you do that, Kimberly? I probably wouldn't. Neither would you. You know what Emil J. Friedrich found out? He said, take Jesse's worst bottle that's poisonous at his house. Take Hannah's most poisonous bottle at her house. Take Megan's most poisonous bottle of thing at her house. Take Courtney's most poisonous thing. Mix them together and drink them. Would you do it, Joe? I probably wouldn't, but this crazy mad scientist thought, hey, let's mix those things all together and we'll will slow down cancer. In fact, in some cases, we can get rid of it. And he was right. Okay? Because he studied the chemistry behind it. He figured out what was going on. So all of those things individually, if you drank them and ate them or put them in your body, they would kill you. But together, he figured out, whoa, these things can save you. Okay? Pretty neat. Bombs are made. Okay? Everything is chemistry. Life, food, death. Okay? Everything is made out of chemistry. So it's something that, I guess you can say, well, this is something we should be interested in. This is something. All right, so let's go on to this idea of, well, let's go back to the 1900s. Okay, let's go back to the 1900s. And there's this crazy idea, because that's what a theory is. It's just an idea somebody has, right? What are some theories maybe out there that somebody might have? Garrett. Okay, explain it.
I believe it's along with the basis of alternate dimensions. Different timelines.
Would you guys believe what Garrett's saying, Courtney? Faith? Who's skeptical about what Garrett's saying over there? But at the same time, a lot of people, I don't know. What's that, Garrett?
I don't believe it.
Garrett says he doesn't believe, but it's a theory. It's an idea. Nobody knows. Well, in the 1900s, there were atomic theories. There was these scientists, and they'd look in these little microscopes, and they'd see these things moving around in there, and they'd be like, now how can they possibly move? They should be sitting still. Well, along came this, I don't know, mad scientist guy, right? Ooh, crazy big-haired Einstein, right? He comes along, and he says, well, I know what is going on here. There must be some other hidden magical particles bouncing around in there and making it hit things, and so there must be very small things we cannot see. Well, guess what everybody said about Einstein, just like Garrett's talking about the string theory, you said? What did everybody say about this guy? Yeah, he's spaced out. He's way out there, man. He's crazy. This theory is just an idea. There's little tiny things we can't see bouncing around in there and hitting it, making it move. Impossible. Okay? Well, he got up here and did his 2 plus 4 plus 8 times x, and then to the square power, and then square root of that. And keep going on with these huge, gigantic math problems that nobody could follow. But in the end, he would go, aha, right here. That's it. There are things called atoms out there. I can prove it with this mathematical formula. What did everyone think? Oh, here's this Einstein guy again, right? Okay. Well, the problem was we didn't have equipment. We didn't have the tools to measure things that small. Okay? That's what was going on at that time. So everybody thought he was crazy. Well, obviously we now know that there are atoms. And then there were some crazy other scientists who said, inside of those atoms there must be even smaller things called, and they named them once they figured out what they figured out, and protons, neutrons, electrons. Okay? In fact, if you go over to Switzerland today, there is this huge billion-dollar tunnel built in a big, huge circle underground. Okay? Why would countries build this billion-dollar, it's called a particle collider? Garrett, you know?
I believe it moves protons and electrons around.
Super fast, okay? And so, like I said, when you get into high school chemistry, you're going to learn there's some other things that are in here too, some smaller things. Anyways, there was these gentlemen, these scientists who got together, they got on their big marker boards or chalkboards, whatever it was they were, and they wrote these huge mathematical formulas, and they said, well, there's even smaller particles out there, and we're going to call them the Higgs boson. And again, and this is in the 2000s. So again, when these guys proposed this theory, what did everybody say about them? Faith? They're nuts. They're crazy. It's impossible. They can't possibly be there. Way too small. No way we could figure it out. Well, billions of dollars later, huge machine that goes around in circles, speeding up electrons at super fast speeds until they finally, bam, run into each other, collide, explode, and they leave all these little particles, and they now have machinery and tools that can find it. Sure enough, a few years ago, sure enough, those things really do exist. Okay? So chemistry, it's That's why you might get the idea of these crazy mad scientists. Maybe you'll be accused of one of them someday. You never know. But it starts out with a theory, and that's where this idea came from. And it was mathematically proven that, yes, protons, neutrons, and electrons do exist. Okay? Basically, they exist in these ball-like thingies with a center that's called a nucleus. And in there are what we're going to call protons, and also in there are what we're going to call neutrons. We're going to save electrons, like I said, for later. We're going to focus on that nucleus. There's protons and neutrons, and these ball thingies all rolling around in there. Okay? Now, I've got an experiment for you to try at home tonight. You think Mom's got an apple in the house? Okay, how about a tomato? Just ice cream buckets at your house, Grant, huh? Ice cream isn't going to help us. We need something solid that we can cut. An onion. How many of you have an onion at home, potentially? Okay, well, whatever it may be. Take an onion, or an apple, or an orange, or something that's pretty solid. Orange is kind of pushing it because they're squishy, and tomatoes too. Stick to apples and oranges. Pears. Cut it in half. Take one half and eat it. Give it to your brother or sister. Whatever. Now you're left with a half. Cut it in half again. Eat one half, get rid of the other. And keep cutting it in half until you get to the tiniest particle you could possibly get to. Are you down to an atom yet? Joe? How do you know? They're not something that's visible to us to see. That's how tiny these things are. That's where the name atom comes from. It's a Greek word meaning invisible. Okay? So, these things are invisible to our eye. So if we were to keep cutting something in half and in half forever, that's what curiosity, that's what drove these crazy mad scientists. That's why when they got to atoms, they said, some people said, we're done. Well, what did the crazy mad scientists say? I wonder if we cut it in half again, if there'd be some smaller things in there. And they did. And then obviously, the next guy said, I wonder if we could cut that in half. So you know out there right now, after the Higgs boson discovery, what are some people going to think about in 10 years, Garrett? Could we cut that in half and see if there's smaller things? Okay? So, we can't get down to this with our naked eye. We need machinery and tools. But try it anyway. See how tiny of a little piece you can get at the dinner table. Just take that knife and just keep cutting in half and half and half to finally get this little fleck that you can barely do anything with. But have some fun with that. Okay? But anyways, an atom really, though, is not divisible. That's why I present this idea of dividing it in half. They can collide them into each other and they'll explode and create huge explosions, which is what an atomic bomb is. Okay? Atomic bomb is a huge explosion when an atom is split in half. Okay? But anyways, it's really impossible to do that. You can't split them in half. All right. Quick stand up. Run around the room for 5 seconds, 10 seconds. Go. We'll see what kind of prior knowledge we have here. All right, find your seats again. What part of an atom were you? You guys were all running way around the outside. What part of an atom would that be? Proton, neutron, or electron? Jesse? Joel? Yeah, they're not labeled up here. We'll get to those. Electrons. You were way on the outside, but we'll come back to them. Okay? Anyways, the number of protons in the middle makes the atom. How many protons are in this one? How many protons did I count? How many little ball thingies are there? Micah? So if we go and look on the periodic table of the elements, which element has a number 4 on it? You can see from there. Garrett? Beryllium. This is beryllium. Okay? This is beryllium. So that is a concept you must understand. The number of protons will equal the element. Whatever, that's all you need. If you can count the number of protons, you can tell me exactly what element this is. You can look at it. It doesn't matter how many electrons it has, and it doesn't matter how many neutrons it has. Okay? But the number of protons is what makes the element. Magnets. How many of you played with magnets before? You guys did that in science, probably in the middle room. When you take a north and you try to push them together on the magnets, what happens? Micah? No, they like to go opposite ways, right? Opposites attract. Well, the same thing is true here in the nucleus. Okay? If in my nucleus I have all these protons, they're all charged the exact same way. Protons have a positive charge. So we want to make sure we get that there. They have a positive charge, protons do. Okay? And so because they all have positive charges, what do they want to do to each other, Logan? Stick together or fly apart? Fly apart. They're just like that north and the north bars on the magnets putting together. They won't go together perfectly. They reject each other. In fact, left like this, they would tear things apart and your whole body would fall apart and everything else, you'd fall apart into a mess. Yeesh. So God created something that we can put in between them. More little bally thingies. And those are the neutrons. Okay? They're basically there to make the protons play nice together. It's like having the babysitter. Mom and Dad can't leave you home alone. You won't get along very well. Somebody's got to keep an eye on you. Haley's got to stay home and watch over Garrett and Brody. Maybe not. I don't know. But anyways, the neutron's job is to make the protons play nice together. They would be bouncing all over the place and falling apart. But when you put neutrons in between them, all of a sudden, the protons are not so excited, and they can stay together in a nice, close-knit ball that obviously we call the nucleus. Okay? All right, I got 6 protons in there. What would this one be? Zoop. Hey, that's a pretty common one. One of the most common elements found on Earth. Can't see it from there. Garrett, help him out. Carbon is number 6. There's 6 protons in here. This is a carbon atom. Okay, we'd have to add some electrons and stuff. Okay? The number of protons is what makes the element. It doesn't matter how many neutrons and electrons it has in it. It changes. So that when we have, let's make one of those squares up here. We're going to change this one. 47. That's its, what we call on one of those squares up there, that's its atomic number. This atomic number is always the number of protons. So what has 47 protons in it? Emma. Silver. This is silver. So what letters should we maybe use for silver? Joel? SL. Ooh, that might be a good one. Is SL taken anywhere else? I don't think it is. Maybe Joe should have designed this table, but unfortunately Joe did not. What letters would you like to use, Logan? I'm picking on the kids far away that can't see. What would you like to use, Logan? What letters should we use for silver? What would be an easy way to remember? SL. Well, Joe said that already, so you can't pick that one. No, you can only pick 2 letters. No, that's what Joe picked. SL. SI. So if we go over here, SI, they've got that. Silicon. When this was made, again, the Latin and Greek language came into play. So the letters for silver are AG. Okay? Argentium. It's a country down in South America known as, Joe? Argentina has a lot of silver. That's how it got its name. It's an old name. So they use the symbol Ag. Now most of them make sense. Carbon C, boron B, oxygen O, nitrogen N, hydrogen, H, helium, He. But obviously they do run out of letters and combinations, so they've got to come up with some that are a little bit different. So for silver, they picked Ag. So the atomic number for silver is 47 because that's the number of protons it has. Okay? If it had 48, we added one more proton, it would be cadmium. If we took one away, it'd be palladium, 46. Okay? So guess what people wanted to do? Gold has 79 protons in it. So guess what people did for years and years and years? Micah? Yeah, they said, oh man, if we can go back to platinum, 78, and we can add one more proton, we can become billionaires. We'll make gold. Or they would go to mercury and say, if we can take one proton away, has it ever worked? Nope. Okay? Nope. Does not work. We can't make those things into gold. It's too difficult. God made things the way that they needed to be, and they can't be changed in that sense. Very, very, very difficult to do. You can't move protons from one to the other. You can move electrons and you can move neutrons real easy, but you can't move protons easy at all. Okay? So, (47) is the number of protons. Take a guess. How many neutrons do you think it needs? Take some guesses. Micah? 1. He says 1 neutron is going to keep all these protons happy from fighting with each other. Emma? 11, she says. Okay. Jesse? How many neutrons do you think? You had your hand raised. She says 20. Logan? 47. Why would you say 47? I know why, but just say it. There's 47 protons, so maybe these 47 neutrons. 48. 1 extra just to get in there, huh? Joe?
36.
He says 36. Micah? Anybody else got one last guess they want to get in? Who hasn't guessed yet? Garrett? 46. Well, ladies and gentlemen, there's no real, there's not a total rhyme or reason that you can follow this. There's actually 60, and sometimes there's 62. Okay, that's how many neutrons are needed to keep 47 protons playing nicely together. Okay? There could be 60, there could be 62. That's what I said. The number of protons cannot change, but neutrons, they can. And each of these is what we call an isotope, meaning if we go into nature, we'll find some silver that will have 60 neutrons in it, and we'll find other bits and pieces of silver that will have 62 neutrons in it. But in the end, the metal is still, Faith, it's still a metal named silver. Yep. Neutrons can change. But there are different isotopes based on the number of neutrons in it. That's why now if we go up here to do a little bit of math, okay, these periodic tables will also have a number. Let's write it in black. Atomic mass or atomic weight. And it will have a number here. And it will usually be a big number. I liked Logan's idea of saying 47, have 1 for each one. Okay. If we go up to hydrogen, we see that the atomic weight is always right here, right under it. So the most common things that you guys are going to need to know are its symbol, its atomic number. Usually they'll put on there its name, silver. And this one last bit and piece of information we need, its atomic weight. Well, the atomic weight for hydrogen is 1.007. Okay, meaning its weight is 1. If we go to oxygen, there's 8 protons, and its atomic weight is 15.994. Well, how do you get an atomic weight, atomic mass? You take the number of protons, plus the number of neutrons. So, how many protons are in silver? Micah? 47. And how many neutrons do we say are in here? So here you get a little choice. Courtney? We're going to go with 60 because that's easy math, right? What's 47 plus 60 equal? Emma? 107. And now let's put the other one right below it. 47 plus 62. What will that equal? Jen? 109. So that means in the world we're going to find silver that has, if we could break down to the one atom, they're going to have an individual mass of 107 or 109. Okay? Well, now let's go look over here. Garrett, maybe you can look over there for silver. Silver here says 107.8682 is its weight. Oops, 8682. So what did they do? Garrett. Nope, good try. It's just kind of an average. They averaged out in nature. What would you find? Well, you would actually find a few more silver atoms that would have 60 than 62, but it usually will be somewhere in the middle. So 108, right? If we rounded this up, it would be 108. Where is 108 found? Right here. Guess what you'll never find in nature, though? Nope. Well, yeah, we'll go. You'll never find one with 61 neutrons. You'll either have 60 or 62, but not 61. Why? I don't know. Go ask a scientist at UW or something, an astrophysicist or somebody along those lines. Not me. But anyways, this number is an average. So that's why when you go up and you look at these things, you see these huge numbers like 1.9 or 192.22. Where'd they come up? Well, all it is they're taking all the different isotopes that are out there, and they're saying this is the average of them. So the weight, you can figure out the weight, or you can figure out the number of neutrons. So let's take one. Let's do this. Stand up. Take your notebook with you. Go over there and just pick one element. Write down its name, its atomic number, its letters, and its atomic weight. Get those 4 bits and pieces of information. Whatever one you would like. Doesn't matter what anybody else is doing, just find one that you like to do. Could be any. Maybe you see californium, or maybe you want einsteinium, or maybe you want to go with simple chlorine, or maybe some neon. You need these 4 things. You need its atomic number. You need its name, actual written out name. You need its symbol, and you need its weight, its atomic weight. It'll be a decimal number, that's okay. Yep, use the map, the chart key. If you want to find out where the atomic number is, it shows where they should be. But the periodic table, the elements is organized. We'll get to that on Wednesday on how it's organized, families and rows and all kinds of stuff there. Similar characteristics. All right, here's what you need to do. So you picked yours out, right? Let me pick one out, and hopefully no one. Did anyone pick radon? Anyone here pick radon? Okay, its atomic number is 86, which means how many protons are in this one, Micah? 86. Radon, very dangerous stuff. It's Rn, right? And its atomic weight, it says, is 222. Okay? So, I know that there are, as Micah said, 86 protons in here. How could I figure out mathematically how many neutrons are in here? What would I have to do? Emma? Take its weight. If we go back to this, we're going backwards. Here's its atomic weight, 107. And we know its number, so we do 107 minus the 47 will leave us with a number of neutrons. So we're going to do that over here. We're going to take 222 minus 86. Okay. So there are 136 neutrons in radon. It takes a lot of neutrons to keep this guy happy. The further you go up, usually the more neutrons they need. Okay? Electrons, we'll get to those at a different time. Okay? So here's what I want you to do that we're going to begin building. I have partnered you up. Find that sheet here with my partner names here a second. Got it. Okay? And here's what you're going to start building. I just want you to, each of you, till recess time here, you are going to creatively come up. It can be with some things in the room, but you have to ask me if you can use them first. Okay? Otherwise, you can come up with some items in the room, or you may come up with some items that you bring from home. But you and your partner are going to eventually build a model of a particular periodic table element. Okay? Now, here's a word of warning. Everyone would think, oh, yeah, let's go cool. Let's go neodymium, man. It's got 60 protons and almost like 80 neutrons. That's going to be huge. Stick to something that's a little bit smaller and easier up there. If somebody else does the exact same one, that's fine with me. Okay? But stick away from hydrogen and helium. Oh, because they just got one. But otherwise, pick something else up there that's maybe a little bit easier to do. You know, your carbons, or your fluorines, or your lithiums. They have 4, 5, 6, 7, 8, 9, 10 electrons, protons, that type of stuff. Because otherwise, you're going to have this huge thing in it. What you could do, which would be really cool, is just going to take you a lot of time. Okay? So that's up to you guys. But that's just my word of warning. Maybe stick to something that doesn't have a huge number because you're going to be scrambling for stuff. So what you're going to do is build a model. Not a draw it on a piece of paper. We'll be doing that later. But not draw, but actually something that you can put together, put some things together. And what you want to start thinking about today is a nucleus. Okay, we need protons and electrons. What can you do? Obviously, well, I could go buy a bunch of apples and stick them together. Those would be the protons. Go buy some oranges, put those in the middle. Okay, I could find these bally figures, or you could just cut out some circles. But anyways, I want it to be an actual object we can hold up and show people and say, these are the protons and these are the neutrons, and eventually we'll add on electrons. Okay? But today you're going to focus on making the nucleus or thinking about that. You might bring some things in. That's got to be done for Wednesday. Okay? So that gives you 2 nights at home to kind of get some things together. You need to communicate with your partner if you're going to do that. You need to say, hey, I'm going to go home and find the marshmallows. We got the pink and green kind. All right. Somebody else says, hey, I'm getting some, hey, I'll go to the store tonight. I can ride my bike, Micah says. I can ride over there, Piggly Wiggly, and I can get some gumdrops. And we can use colored gumdrops. Could be anything, whatever you guys want to come up with. Okay? But you decide what it is that you are going to use, and it's got to be something that we can hold together. We can make it stick together with glue or other things like that, just so that we have an actual atomic model of a nucleus right now, just protons and neutrons. And it has to be accurate. So when I come by and I see, hey, this has got 8 protons in it, well, I know this is oxygen. So I can go up there and look at, well, it's about 16, so it should have 8 neutrons in it as well. It better be accurate. Okay, that's what you're going to be measured on, is how accurately you did it. Neatness and that kind of stuff too. Okay? So, Garrett, you're going to work with Kimberly. Grant, you're going to work with Jen. Jesse, you're going to work with Megan. Hannah, you're going to work with Micah. Faith, you're going to work with Logan. Courtney with Joe. And Emma with Kenton. He's not here. Maybe you can send him an email. But anyways, you'll still have, hopefully he'll be here tomorrow, but we can start getting going on that for Wednesday. Okay?